All right, so for this lesson, this is topic 8.2. We are going to build off of what we began on the prior lesson with our introduction to Avogadro's constant, how we work with Avogadro's constant, and how we work with molar mass. And today we're going to kind of work on connecting the two topics. So the first thing is I'm going to provide you a kind of cheat sheet. This is not going to be available for quizzes or tests. You can definitely draw this on to a quiz or test as kind of a quote unquote brain dump. But what this does is kind of gives us a little bit of a what I call the mole map, in that it gives us a place on what to do and what to use based on givens and what we're solving for. So the whole idea is the mole allows us to convert to three things. We're not going to talk about volume of gas just yet, but we have talked about these two things. So the first thing is representative particles. There's three options depending on what it is you're counting. If you're talking about something held together with covalent bonds, that is sharing of electrons, and we call those molecules. The Hoffenkleiber diatomics count as this. Things like water and carbon dioxide also count as this. Formula units are those that are held together with ionic. So things like table salt, sodium chloride, or silver sulfate or silver 1-nitrate would all be formula units because they are a metal, nonmetal, cation, anion. And then elements that are not diatomic are then counted in atoms. Those representative particles apply to Avogadro's constant. So depending on what direction you're going, we know that a conversion factor has two ways to be set up. So if you are starting with one of these representative particles, for example, molecules, to go from molecules to the mole, you would use a conversion factor setup like this. I had to leave this part blank, Avogadro's constant, because you can substitute in one of these three options as our unit. That converts to moles. If you want to go from moles to representative particles, like we did with yesterday's notes, the first portion, you then multiply by Avogadro's constant. So these are the two ways in which the conversion factor can be arranged depending on what you're solving for. Now, the other half of this bridge that we worked on was the whole idea of mass. If you're starting with grams and wanting to go to mole, or if you have X number of moles and you want to figure out grams. Here, we needed to calculate molar mass. The unit for molar mass is grams per mole. Okay? We used our periodic table to look up masses. Some of the examples were those of elements where we just had to find them and round to 2 decimal places, and some involved a little bit more of a calculation because they were compounds. One of the things we'll review is molar mass of compounds, okay? So I'm going to refer to this off and on because what we're going to do today is connect both towns on our mole map, the towns being mass and representative particle, all right? So I've kind of explained this first one, and again, through examples, it'll explain that first part of the notes. So, like we began, we have a given, and we have what we're trying to solve for. It says convert 83.2 grams of chlorine. So not only the amount and unit of what we're given, but what it's of is important. We want to figure out how many molecules this is, okay? So what we need to look at to decide is how many steps are necessary to solve. Our mole map tells us that. We are starting here at mass because I have grams. We want to get to molecules, which is one of the three types of representative particles. That means 2 steps are involved in the process to solve. There is no direct relationship between mass and particles. The intermediate step is to go through and go to moles. So there's 2 conversion factors needed. The first conversion factor is to eliminate grams, and that's through the use of molar mass. So the next thing you have to understand is what is the formula for chlorine? Chlorine is Hoffenkleiber, meaning it's diatomic. So the formula is Cl2, not just Cl. That means when we go to find our molar mass using the periodic table, we find that it's 35.45. But our subscript is implying that there is 2 of them there. So we would take 2 times 35.45 and get a grand total of 70.90 grams per mole. Again, you can just cut this off at 2 decimal places and not have to worry about having more than that, okay? So, as I just stated, our given unit was the 83.2 grams of chlorine. It's critical that you label it with the unit that you're in, but not just that. I will find, and you will find, that it's important to label it with what it is as we make our way forward. Okay. We know that starting with our map, if we are starting with grams, we need to convert to moles. We found molar mass, and now we know how to set up our conversions. The 70.90 grams is the denominator, and 1 mole is my numerator. Again, what I can see here is that grams canceled. Everything we did yesterday was a one-step problem. This is not going to be a one-step problem. We haven't solved for what it asked for because we ended at the mole. We need to get it out to its representative particle of molecules. We did two-step conversion. So what we need to do is add a second conversion factor. Our representative particle has 3 options for labels, and because molecule is applied to chlorine, we're going to use that as our label. We're going here from the mole out to representative particle through the use of Avogadro's constant. I see that because, again, I have mole here, therefore I need to divide by 1 mole. Avogadro's constant, again, is my numerator, and I can abbreviate it as MQL, showing that units have canceled. I'm going to get my calculator out so you guys can see how I typed it in. There's more than one correct way to go about typing this into your calculator. It's going to be your personal preference. I like to just go conversion factor by conversion factor. What I mean by that is I would type in 83.2, which while I'm talking about it has 3 sig figs. I'm going to divide by 70.90. Do not worry about rounding sig figs until you're done with your calculation. Then I'm just going to multiply that by 6.022 to the 23rd. Now I want to think about sig figs. So I end up with 7.06 with a rounding. I would get 7.07. And again, especially for those of you with graphers, make sure you look for that E. So 7.07 times 10 to the 23rd. Looking back at what our units were provided to us here would be MQLs of chlorine, and we're done. So again, based on my mole map and my understanding of the relationships, this told me I needed 2 steps in order to solve. So we're connecting the 2 things we just began with. Okay, continuing on. Here it asks, how many grams are in 3.34 times 10 to the 34th formula units of copper, Roman numeral 2, hydroxide? As we've done, establishing what I have. I have 3.34 to the 34th formula units, and also what it's of is the copper 2 hydroxide. We want to change it to grams. Let's talk about the formula of our compound. We know copper is Cu, and we know that Roman numeral is the charge of copper, plus 2. Hydroxide, referring to my polyatomic list, you would find that it's OH minus 1. So when you cross through charges, you would get Cu, OH2. I would encourage you, when you go to find molar mass, I would take an inventory as we get started. We have copper, we have oxygen, and we have hydrogen. We have 1 copper. This 2 distributes into each element, just like distribution in math. So 2 oxygen and 2 hydrogen. I then go and find each of their individual masses according to the periodic table. Again, rounding it off after 2 places. 63.55 is copper. Oxygen rounds to 16. And hydrogen, it's your preference, but a lot of times we just use 1 flat and call it good. So we just have to multiply and add things up. So 63.55 is going to get added to 32 and 2. I just multiplied these in my head. My grand total is 97.55 grams per mole. Again, the reason why I knew I needed this right out of the gate is that I'm solving for grams. Again, if you start with grams or end with grams, you need molar mass, so I was just getting that out of the way. Let's talk about our given. We have 3.34 times 10 to the 34th formula units. And this is copper 2 hydroxide. Okay. When we go to look at our map, if we're not sure what to do, we have formula units, which is one of the 3 representative particles. We need to get it to grams. So this problem is just an inverse of what we just completed. The idea is, in order to get from here to here, there's no direct relationship. The only way to get to that point on the map is through the mole. And to get from there, the use of Avogadro's constant. I'm going from formula units to moles. This is the conversion factor that would apply. Again, that reaffirms that I have formula units. I have to divide by formula units. So I would take Avogadro's constant of 6.022 times 10 to the 23rd is equal to 1 mole. That allows formula units to cancel, and I'm at the mole, as the map stated I would be. From there, I need to get to mass. In order to get from here to here, following my directional arrows, I need molar mass. I already have that done. In order to make units align, I'm going to divide by 1 mole, and I'm going to multiply by 97.55. I see that my units have canceled orderly, and that I got what I'm asked for. I have a unit of grams. Again, you can type this in multiple ways. I'm going to take 3.34 with 3 sig figs to the 34th power. I'm going to divide that by Avogadro's constant, and then I'm going to times that by its molar mass. When I get to the end here, I see that I, again, have a number that's in scientific notation. This is a rather large number. So I have 5.41 to give me my 3 sig figs times 10 to the 12th power. I'm left with grams, and I'm going to label it with the copper 2 hydroxide. And that's my final answer. And this is how we go from particles to molar mass. Okay. If I look at the next example, it asks, what's the mass of a sample consisting of 1.00 times 10 to the 22nd for formula units of magnesium sulfate? Okay. So here with this example, identifying my given as the 1.00 to the 22nd, and it's of magnesium sulfate. It tells me I want mass, meaning grams. Looking at my map, I'm at formula units, a representative particle, and like the last problem, we need to get to mass. So we're going to find there's a lot of things similar. Okay. So to start, it tells me to get from particles to mole, I need to use Avogadro's constant, specifically dividing by it. So I'm going to go ahead and write out my given. Okay. And then I'm going to step away for a second and talk about the formula. Magnesium. We know magnesium is Mg. There goes my pen. And sulfate is SO4. Thinking about charges, magnesium is a +2. Sulfate's a -2. So the compound I'm working here with is MgSO4. I'll need that for showing in my work and as I work through. This is also 3 sig figs. We saw with the map we need to use Avogadro's constant, and we're dividing by Avogadro's constant to make formula units cancel. And that's always equivalent to 1 mole. I can show the canceling of formula units, and I know that I'm not done because it's asking for mass, and the unit for mass is grams, not the mole. We can refer to our map Let's see, I dropped my pen. I'm trying to get it. There we go. So we're trying to look at our map. We're here at the mole, and we're trying to get here to mass. We need the molar mass. We have MgSO4 as our formula. So it's composed of magnesium, one of them, sulfur, one of them, and oxygen is 4. Then you can refer to your periodic table to get their individual masses. Magnesium is approximately 24.31. Sulfur is approximately 32.07. And oxygen again rounds to 16. So we're multiplying and adding the 3 up. So through that, I have 24.31 plus 32.07 because multiplying them by 1 is going to do nothing for that. And accounting for the 4 oxygen. My molar mass is 120.38. It's grams per mole. Okay. So from there, I am ready to go ahead and plug in. I know that I have moles here. Therefore, I need to divide by the mole portion of my molar mass. And that tells me that my mass of, let's see here, the MgSO4, the 120.38 is my numerator. And I see the elimination of moles. We divide. Using that EE function. And timesing by our mass of 120.38. We can keep 3 sig figs, and I have a little bit of a domino effect here. So it's going to end up kind of pushing and rounding as it goes. So I'm going to say my answer here is going to be 2.00. And this is grams, and I'm going to include that this is magnesium sulfate. So again, your units tell you if you need 1 or 2 steps. One of the things I would encourage you is on your homework, not each problem will need 2 steps. Some only need 1. Use your map, and that will decide if it's a 1-step problem or a 2-step problem.